So I want to do now for each of these examples, remember, is I want to determine the domain and range. I also want to draw a correspondence diagram. And we're also going to see if the relation is a function. Okay? Excuse me. That's what we're going to see. So let's do that. So for the first example, I mean, even without drawing a correspondence diagram, even really without doing anything, you should be able to tell that this is a function. Because all the ordered pairs here, as you can see, all of them, okay, have different first x coordinates. They have different x coordinates. You know, here you have 1, here you have 2, and here you have 3. So because of that, that's how you know it's a function. I mean, basically what's going to happen is something like this. Each input is only going to have one output. Each input's only going to have one output. So 1 only has 5. And because this ordered pair is here, I draw the arrow, like C. Here, I draw the arrow from 2 to 12, okay? Right, and 2 as your input has output 12. 3 has input, as you can see. 3 is input, as you can see, and has output 20. But you can see that each input here has only one output. Right? One arrow is only coming out of each of these. So that's how we know it's a function. Building on that, the domain, as you can see, is 1, 2, and 3. Okay, that's all the x coordinates, which I have in here. So not only that, the range is 5, 12, and 20. Excuse me. So what we have then is 5, 12, and 20. That's the range, the y coordinates, and that's in our second set. So for the second example here, I mean, again, you can tell it's not a function. You have 2 ordered pairs. Actually, you know what, before that, here, let's do this. So I went back to this one instead, but you can tell this is not a function. And why is that? Well, you have 2 ordered pairs here with the same x coordinates. You know, both of them are 5. And that's telling us 5 as our input has 2 different outputs, 9 and 10. So this is not a function. The relation, so in relations, there are assignments like this. Like 5 is assigned to 9. It's also assigned to 10. Okay, you can see that 10, 7 is an ordered pair in here. So 10 is assigned to 7. Okay, 1500 is in here. So 15 is assigned to 100, but it's not a function. You can see here that there are 2 arrows coming out of 5. Okay, there are 2 arrows coming out of 5. So 5 has 2 different outputs. You can't have that in a function, so it's not a function. That's what I'm saying down here. Also, the domain is all the x coordinates, you know, everything we listed here. We have 5, 10, and 15, as you can see. Right? We don't only list 5 once. I know it's here, it's in 2 different ordered pairs, but in a set, you only list it once. I mean, if you happen to list it twice on a quiz or something or exam, you know, I'm not going to take points off. But you really should just list it once. Now for the range, this is all the y coordinates, okay? That's what the range is. You know, everything in here. So we have 9, 10, 7, 100, right? All the outputs. The range of this relation, you know, relations can have domains and ranges, okay? They can. So the range would be this, as you can see. Okay. So that's this example. For the third one, as you can see, we have this, right? So we have these ordered pairs. I draw the correspondence diagrams, right? I mean, here I'm not drawing it by hand, which is probably good because this is better than my handwriting. But we have 2, 8, no, excuse me, we have 2, 12, 4, 7, as you can see. And 2 goes to 8. So 2, we have an arrow from 2 to 8. We have an arrow from 12 to 100. That's what this is doing. 4 is going to 2, as you can see. 7 is also going to 8. Okay? 7 is going to 8. Right. Yeah. Okay, so that's what we have here. Now notice, though, that this is a function. All the ordered pairs have different x coordinates. And you can also see that each input only has one arrow coming out of it. See? One arrow coming out of it. One arrow, as you can see. So even though you have 2 and 7 having the same output, that can happen. That's okay. We still have a function. And the domain of this relation is 2, 12, 4, and 7, as you can see here. And the range, right, is all the y coordinates, 8, 100, and 2, and 8. But 8, we only list once. Even though I wrote it in this order, it really doesn't matter what order I write it in. Remember, in a set, the order doesn't make a difference. So I could write this as 100, 8, and 2. I could change the order, in other words, and that won't make a difference. Okay. All right, so we have those examples. Let me just ask this. Here, okay. Yeah, I taught this class before without using correspondence diagrams. I really think they help. At least I hope they do. I know the book does them, so I really hope this is making sense for everyone. Yahoo! Looks like everyone is, almost everyone. Well, people are responding yes, so I'm happy. Awesome. All right, so so let's keep going then. I actually did a little bit of what I'm about to talk about next, which is the graphing and vertical line test. In other words, you can also get a function from a graph. I mean, really, if you think about it, what is a relation? A relation is just a collection, a set of ordered pairs. What is a graph? A graph is just a collection of ordered pairs, or points, in other words, plotted in the plane. So there is a connection between relations and graphs. Namely, from any relation, you can sketch a graph. And the other way around as well. In fact, if any of us draw a graph in the plane, Cartesian plane that is, we can form a relation out of that. I mean, it may not be easy to do because most graphs have infinitely many points, but theoretically we can form a relation. So just like a relation, from a relation we can get a function, we can also get a function from a graph. And how do we do that? That's where this vertical line test comes into play. Okay? Namely, the vertical line test is used to determine if a graph sketched in the Cartesian plane defines a function. That is, if it's the graph of a function. Namely, what has to happen is this. A graph in the plane is the graph of a function exactly when no vertical line intersects the graph more than once. In other words, every vertical line you draw in the plane is either not going to intersect the graph or intersect the graph once. If that happens, then the graph is the graph of a function. In other words, in such a case, every point on the graph you could think of as giving you function outputs. In other words, every point on the graph looks like this, is of this form. Where f is that function. So f, I'm just using that to denote the function. Okay? I mean, again, from the notation we did, you can use f, g, or h. From the context, it will be clear, or should be clear. But if a graph passes the vertical line test, then we have this. Then the graph defines a function, and every point on that graph is of this form. That has to happen. Okay, let me stop the recording.